On May 12, 2021, researchers at the Howard Hughes Medical Center published research showing a 65-year-old man suffering from paralysis typing up to 90 characters per minute using just his mind. This is comparable to typical smartphone typing speeds, and the accuracy of the typed words was 99% when combined with a standard keyboard autocorrect system. Previous records for systems like the P300 Speller were around 30 characters a minute, so this is a huge leap forward for communication of motor impaired individuals. Using the invasive braingate brain-computer interface, the subject was tasked with attempting to handwrite different sentences. The team's findings may pave the way for improved accuracy of future BCI systems. The researchers at the Howard Hughes Medical Center were curious as to whether or not highly dexterous motor skills, such as handwriting, remained intact when an individual underwent paralysis. To the shock of all those involved in the study, they found that these advanced motor tasks were, in fact, preserved. Despite years without use, they were able to capture high-quality signals from areas of the brain that the subject had not used since his injury. The scientists used two microelectrode arrays placed in the precentral gyrus, which is a premotor area of the brain. Specifically, they wanted to target the area of the precentral gyrus that has to do with dexterous hand movements. They then asked the subject to attempt handwriting individual letters and symbols in the same way he might if he was not paralyzed. In the experiment, the subject was tasked with imagining his hand writing the letters, and the computer system would then display that letter for him. Principal component analysis was then used to analyze the brain signals collected from the microelectrode grids. Principal component analysis, essentially, reduces the number of variables in a dataset while preserving as much vital information as possible. This technique is especially useful for brain-computer interfacing systems, as researchers tend to receive large sums of data from their recording techniques that are not easily understood. The researchers then massaged and cleaned the data with more advanced reduction methods, notably T-distributed stochastic neighboring embedding, and found tight clusters of neural activity for each of the letters in question. Essentially, they were able to find within the neural data small clusters of neurons which represented different letters. So, one cluster may represent the letter A, while another cluster may represent the letter Z. Incredibly, they were able to classify each letter with 94% accuracy. This discovery demonstrates that even after paralysis, dexterous skills such as handwriting are preserved in the motor cortex. Using these unique clusters of neurons, they were able to create a map of the different handwritten letters. But the real magic happened when the researchers combined this newfound map with other techniques to allow the subject to write full sentences with only his brain. Once the letters had been properly mapped by the implanted electrode system, the subject was tasked with handwriting complete sentences at his own pace. The computer system would provide instructions, and the subject produced a total of 242 different sentences over 3 days. The data from the BrainGate BCI was then fed into a recurrent neural network in an attempt to decode the data in real time. They called this bit the decoder. Recurrent neural networks are commonly used in artificial intelligence, such as Apple's Siri and Google's voice search. They're a unique algorithm because they can remember input, which is incredibly useful in many common machine learning tasks. Recurrent neural networks require a lot of training and computation, and they can sometimes be slow. But with large amounts of data and time, they're able to grow in accuracy and create some really astonishing results. The researchers then used retraining methods on the decoder to help calibrate the model between different sessions, which also improved the robustness and accuracy of the model. The accuracy of the model for handwritten tasks was between 94 to 99%. However, they did notice that the error rates of the model grew as time between the sessions increased. For example, they would notice a higher rate of errors if 7 days passed since the previous session. The BrainGate system, which was used in this study, utilized two implantable microelectrode grids. These grids were placed on the cerebral cortex of the subject, and the microelectrode grids were connected to an external processor, which cleaned and sent the neural data to the researchers' computers. Invasive systems like this are highly accurate when used correctly, but they're generally reserved for individuals who are suffering from motor disabilities. This is because these systems are difficult to install and may have many unforeseen health risks to the subject in question. Because of this, invasive systems are not very common. At least they're not very common yet. In comparison, non-invasive techniques, like electroencephalography, suffer from loss of data accuracy, but they don't require brain surgery to use. Some non-invasive techniques may not suffer from as much loss of data, but they require large, unwieldy machines that have to be magnetically isolated to work. These systems will undoubtedly continue to improve over time, but invasive technologies have shown more promise for their high accuracy data acquisition so far. Hopefully in the future, it will be possible to get the same quality of data from non-invasive systems. But for now, invasive systems still reign supreme. Thanks for sticking around, and if you enjoyed this video, please remember to like, comment, and subscribe. If you're interested in supporting us in making more educational neurotechnology content and help us pay our amazing video editor Mike, consider supporting us on Patreon or checking out our merch store at bciguys.com/support. Thanks again, and we'll see you in the next video.